Hello students, today we could learn about the modeling of, or let's say the representation of the basic throughput machines for uh, some machines like three-phase induction machine and Cron's primitive machine. So let us start with three-phase induction machine. As you can see in the figure, uh, outside the rotor there are three windings, capital A, B and C, and inside the rotor there are three windings, small a, small b and small c. So the capital A, B, C are the three coils of the stator winding. Just for convenience, the winding A is taken along the D axis. You can also take either B or even C on the D axis. So here capital A is taken as on the D axis. Now as you can see, we have small a, small b and small c. All of them are behind the D axis by a particular angle. So the same angle could be seen between capital B and small b and capital C and small c. Now the thing is, why is this behind this particular A? Why is it not ahead of particular A? So the reason behind is the uh, MMF which is produced in the rotor winding is because of the stator winding, so it would always lag behind the field of the stator winding, and that is why it is drawn behind. So irrespective of your rotor being a slip ring rotor or say a squirrel cage rotor, this is how would be the basic two-pole representation of your three-phase induction motor. So, in general, we can say that there are a few things that have to be kept in mind before drawing this particular diagrams. So, what all things you should know, like the stator and the rotor configurations. The second thing that you should know is the winding arrangement of both stator and the rotor. The last is the position of the brushes. In this particular case, in this particular machine, you don't have any brushes. So the third point does not, come to. So the third point does not come into the picture because you do not have any brushes in this particular machine, but where the brushes are applicable, so based on that you will make a decision. Next we'll move to Cron's primitive machine. So in a Cron's primitive machine, as you can see in this particular figure, we have DS and QS, which are nothing but the field winding on the direct axis and the field winding on the quadrature axis. So, and we can see that there are four brushes, or you can say two pair of brushes. This is one pair and this is the second pair. Now the interesting thing is both the brushes are perpendicular to each other. The both set of brushes are perpendicular to each other. Now you can simply draw this in the two-pole representation as the DS is as it is. Because of these two brushes we have a winding DR. Because of these two brushes we have a winding QR, and QS is as it is. So I hope you're able to understand that what would be the uh, you know how the windings are being placed. Fine. So now we'll move ahead to the text, which says the idealized or the basic two-pole machine diagram of this machine can be easily drawn, and it is as shown in figure 1.15b. This is what we have already seen. This equivalent circuit network is called the generalized machine, or the Cron's primitive machine, or the generalized model or two-axis model of the rotating electrical machines. It is to be noted that the armature coils, that is dr, which is along the d-axis, and qr, which is along the quadrature or the q-axis, have they produce stationary flux along the brush axis, but this is only when the brushes are stationary. The brush axis can also be called as commutator axis, but what if the brushes are rotating? So if the brushes are rotating, then uh, the flux, or let's say the armature flux, will also be rotating. Now this uh, Cron's primitive machine is shown as the equivalent to any of the rotating electrical machine, and the reason behind uh, is because any particular type of machines could be represented by this Cron's primitive machine with a certain combinations or transformations, as well as certain addition and elimination of certain coils. Now let's say for an example of a DC machine, we have only a field winding and a rotor winding. So we'll only have DS and QR. The DR and QS winding would be eliminated from there. So the normal DC machine could be symbolized out of this two-pole representation of a Cron's primitive machine. Similarly, we can see such things for other equipments as well, other machines as well. For example, for an amplifying machine, we need to remove the QS, but simultaneously we'll also have to add the compensation winding, that would be DC, which would be along the D axis. Now we have seen the representation of amplifying machine in the previous lecture, so you can recall from that. So some of the basic two-pole machines are similar to the generalized or the primitive machines, but if they are not, it is necessary to make a conversion. The process of conversion from the actual coils of the machine itself to the equivalent DQ axis of the generalized machine, or the other way around, that is from dq to the actual axis, is known as transformation. Let's say, for example, in a three-phase winding on the stator, the transformation must be made to the equivalent ds and qs in such a manner that the magnitude and direction of the mmf by the three-phase currents, that is Ia, Ib, and Ic, and the two currents IDS and IQS is identical. So that means the rotor of this machine should work in the same manner whether you are providing the phase currents IA, IB and IC, or you are providing the currents IDS and IQS. So the machine should behave in the same way. Now we need to know that there are no electrical connections between the windings of the Cron primitive machine, but there are certain assumptions that we are required to use the primitive machine. The first assumption is the MMF distribution along the air gap periphery is sinusoidal. We keep that in mind that we are talking about the sinusoidal distribution in the air gap. This effectively neglects the space harmonics and their effects on torque and on induced voltages. The second assumption is the saturation and the hysteresis are neglected. So that means the linear coupled circuit theory is assumed to be valid, and the slot do not cause appreciable variations of inductances with the relative movement between the stator and the rotor. This, along with it means that self and the mutual inductances vary simultaneously as the rotor moves. So these are certain assumptions that needs to be kept in mind before selecting the primitive machine, or let's say the use of primitive machines. So I hope you are clear with this Cron's primitive machine. So let us have a complete overview of the entire uh, the basic two-pole machine representation. We started with the commutator machines, and we saw certain diagrams for the separately excited DC motors, its representation and its basic two-pole representation, where we had seen the field winding DS for the separately excited machines and the rotor winding as QR, which is on the quadrature axis, and the field winding is on the D axis, so that is DS. Secondly, we had seen the next machine, and which was a DC compound machine. Irrespective of the compound machine being short shunt or long shunt, or whether let us say it is differential compound or integral compound, we have seen the diagram where we have seen DSE, that is the series field winding, being in connection with the original field winding, and the rotor winding remains as it is. Now, we had also seen that the series field winding could be shown on any of the ends, either on the right end or the left end, which is as shown in the figure B. But the conventional way is showing as shown in the figure 1, or say the figure A. So after that, we had seen the DC machines with interpoles, where another small pole is kept between the two poles, and so that is, it is kept at 90 degrees, and as we had discussed that it was 90 degrees electrical, not 90 degrees mechanical. So here what we are doing is from D axis, if we go towards q axis, so that is 90 degree, and that is why qs is placed here on the q axis. So that is what was about the DC machines, the DC compound machines. Next, we had seen about the amplitude machines. We had seen how the compensation winding and the field winding are placed together on the d-axis, as well as we have the brushes which are placed on the d-axis. So we have a dr winding here, whereas another pair of brushes which are short circuited and placed on q axis, so we have a qr winding here. Next, we have talked about a single phase AC series machine. So we have seen that a single phase AC series machine has a field winding here, so that is DS, which is providing the MF across the D axis, and a pair of brushes along the Q axis, so we have QR here. Next, we have seen a repulsion motor where the brushes are kept at an angle alpha from the direct temperature axis, and the brushes are again short circuited. So we have AR along the angle alpha from the D axis, and the field winding as it is on the D axis, we have DS along the D axis. Then we have seen synchronous machine with and without dampers. So irrespective of the armature being on the stator or rotor, or the field winding being on the stator or the rotor, we are more interested in the relative difference between them, or let's say the relative motion difference between them. So here we have again taken A, B, and C on the rotor, and we have taken field winding along the D axis of the machine. So when we are considering the compensation part with the dampers, so the damper winding has KD factor and KQ factor coming along the D axis and Q axis respectively. Then moving ahead with the three-phase induction machine, we have seen how a three-phase induction machine uh, works, and we have seen how the stator and the rotor elements can be shown irrespective of whether it is a slip ring induction motor or a squirrel cage induction motor. Then moving ahead, finally we have seen the Cron's primitive machine, and how the machine are represented, and how why is it called a generalized machine, because they could all the machines, mostly all the machines could be represented by using Cron's primitive machine. The only thing is you'll need to make certain changes, like adding a couple of winding or removing a couple of winding as per the machine you have selected. So apart from that, it serves the major um, it serves the major aspect of representing most of the machines. So that is why it is also known as the generalized machine theory. So that's all for today's session. Uh, Hope you are understanding the topics well. Feel free to mail or even comment in the comment sections for your queries, or reach out to me on the email address provided in the description section. Thank you and have a great day.